Correlation. The word correlation is made up of co, meaning together, and relation. A statistical method used to determine whether a linear relationship or a linear correlation exists between two variables. The data can be represented by order pairs, your x and your y, where the x is the independent or explanatory variable, and the y is the dependent or response variable. Key note here is correlation does not mean causation. So if you have a correlation, it's not necessarily that we have a causation. A scatter plot, also known as scatter diagram or scattergram, graphically depicts the relationship between two variables in a two-dimensional space. So you see a table of values, your x values and y values, and you see what the picture for that table of values would look like. The scatter plot also shows correlation between the variables, providing information about how closely they connect to each other. So the types of correlation, determining the correlation of your x and your y. The first type is when you have your correlation or the points that are plotted going in the upward direction, it's considered a positive linear correlation. So as x increases, your y tends to increase. When your points on the graph are going in a downward, it is considered a negative linear correlation. So what's happening is as x increases, your y values tend to decrease. If you have a scatter plot where the points are all over the place, then there's no correlation. And then lastly, if you have a scatter plot where it is shaped as a curve, then it's not linear, so it's a nonlinear correlation. So there's three types of positive correlation. The first type is a perfect positive correlation, and that is when your graph creates a line in a positive direction. There's the high positive correlation, and that is when the graph is going in a positive direction and the points are closely gathered together. And then there's a low positive correlation where the graph is going in an upward direction, but the points are scattered out a little further. And it works the same way with the negative correlation, except for the graphs will be going in the downward direction. So there's perfect negative correlation when the points are very close together to a straight line, high when they're close together but still scattered a little, and then lastly low when they're scattered out but they are still forming a downward direction. So how do we create a scatter plot? Well, we're going to be doing it in our calculators, the 83 or 84. So here we have an example of a table for heights in inches and weights in pounds of 7 randomly selected players on the Chicago Cubs active roster. So the x value is my height and the y value is my weight. So before we can do anything in this correlation and regression chapter with our calculators, you have to make sure the diagnostic is on. So to do that, you want to go to your second button and choose 0. You see above the 0 in writing, you have the word catalog, and you want to arrow down until you find the diagnostic on. Once you get it highlighted, you hit enter and it will turn the diagnostic on. We only have to do this once. Once you turn it on, it will stay on. So now to get the scatter plot, you're going to enter in the data into your calculator. To do that, you go to your stat key, hit number 1, which is edit, and then type in the x values into your list 1 and your y values into your list 2. Once you have the data entered in, then you're going to go to your second y equals, and then you see above the y equals that stat plot. So you're going to hit enter, and then you're going to come to this menu where you're going to choose number 1, and then you're going to see this view in your calculator. So you want to make sure that the plot is on, so highlight on and hit enter. And then the type that you want is the first type, which is the scatter plot. So make sure that's highlighted, and then the X list is your L1, the Y list is your L2, and the mark, choose the first mark when you do the graph. And then you're going to hit zoom, and the zoom button is at the top middle, and choose number 9, or the one that states zoom stat. So zoom stat will give us our scatter plot. So this is what this scatter plot would look like for this data. Pause and try. So this is what you should see in your calculator. It's a positive correlation. So when we talk about correlation, there's a correlation coefficient, and it's also known as the Pearson coefficient. And it measures the nature and the strength between two variables of the quantitative type in a sample. So the symbol would be a lowercase r for the correlation coefficient. The sign, whether it's positive or negative, for the correlation coefficient denotes the nature of the association. And then the value of the r denotes the strength of the association. All correlation coefficients will be between a -1 and 1. And the formula to find the correlation coefficient is shown here. So the correlation coefficient is associated with our x values and our y values. Now we're going to be able to do this in our calculators, but this is what you would have to do manually to find the correlation coefficient. Now when we're working with hypotheses test, we're always working with hypotheses test and the population. So for the population correlation coefficient, it is represented with the symbol rho. So the correlation coefficient again is between a -1 and 1, and the strength of the association of scale measures if you have a +1, it's considered a perfect positive correlation. If you have a -1, it's considered a perfect negative correlation. If you get a value of 0, then there's no correlation. So interpret the correlation coefficient R in terms of variance. So a key note here is the closer our R value is to a positive or a -1, the stronger the evidence of a relationship. So let's see some pictures here, examples of what the R value looks like in a picture format. So if we have an R value that equals a -0.91, well, we have a negative correlation, and it's considered to be a strong negative correlation. So you see here the graph has our points very close together going down in the negative direction. If you have a positive 0.88 as our R value, well, that means that we have a strong positive correlation. And you see the graph depicted here is our scatter plot has the points closely together going in the upward direction. And then when you have a scatter plot or an R value where it equals 0.42, well, you see the scatter plot, the points are scattered out. So this would be a weak positive correlation because our value is positive, but the value is low, so it's considered weak. And then when you have a value for R equal to 0.07, that would be considered no correlation. So looking at the scale at the bottom here, you can see that if we have a value from a -1 to a -0.5, it would be considered a strong negative correlation. But between a -0.5 to 0, it would be considered weak negative correlation or no correlation. And the same goes for the positive correlation. From 0.5, positive 0.5 to positive 1, it would be considered a strong positive correlation, but between the 0 and 0.5, it's considered weak. So the linear correlation R rounding rule. Rounding the linear correlation to 3 decimal places so that its value can be directly compared to a critical value. So finding the correlation coefficient using our calculators. So we have the same table here from the previous example that we did the scatter plot for. So now we want to calculate the sample correlation and describe the type of correlation we have. So the first thing, you're going to enter the information into the calculator by doing what we did to find the scatter plot. You're going to go into Stat, hit Enter, and you're going to enter in list 1 your X values and list 2 your Y values. Once you have the list entered into the calculator, you're going to want to calculate. And you're going to go to the Stat button again, arrow over to Calculate, and you want to choose number 4, the lin, reg, and the parentheses AX plus B. That's going to give us our linear correlation coefficient. So it's most calculators, it's the number 4. If it's not number 4 in yours, you want to make sure you're choosing the right menu option. So if you have a newer calculator, you're going to see a picture that has the X list, the Y list, and you want to make sure that L1 is put in and L2 is put into the Y list. Now if you have an older calculator, you're going to need to type in, once you hit enter, you're going to see the lin reg, and you're going to have to enter in the L1, L2. And you can find that option above the number 1 and the number 2 in the calculator, and you're going to have to use your second key to get to it. Once you get that in there, you're going to hit enter, and you're going to find that the R, or our correlation coefficient, R, will equal 0.726. Now what this means is we have a strong positive linear correlation. As the height increases, the weight will increase. Pause and try. Here you should have gotten a correlation coefficient of 0.880, which means it's a strong positive linear correlation. As age increases, salary increases. Linear regression. In a correlation, the 2 variables are treated as equals. In regression, one variable is considered independent, predictor, or explanatory variable, and that'll be the X variable, and the other, the dependent, or the response or outcome variable, which is your Y value or the Y hat. Because we're dealing with samples here, we're going to be talking about a Y hat versus simply Y. After verifying the linear correlation R between the 2 variables is significant, meaning it's either positive or negative, no correlation, it wouldn't be significant. Next, we would determine the equation of the line that best models the data, known as the regression line or the line of best fit. The equation can be used to predict the values of your Y hat for a given value of X. So here are the regression equation line of best fit, the different ways that we might see it. So the equation of regression line for an independent variable X and a dependent variable Y is, in algebra, where it's known as the slope-intercept form, where you have Y equals mx plus b. In our calculators, we'll see it as Y equals ax plus b, or it might be switched around where you see Y equals a plus bx. And then in our statistical textbooks, a lot of textbooks use the Y equals b sub 0 plus b1 x. So they're all the same equation, and what you need to know is that the slope of the line is always the coefficient of the x variable, and then the y-intercept will be the constant of the equation. So if you're asked to predict and you're given an equation, so we're predicting the y value using the regression equation. And in this example, we're given the regression equation, but we're going to be finding it with our calculators. So this is a regression equation for the gross domestic product in trillions of dollars and the carbon dioxide emissions in millions of metric tons. And here's our equation. Use the equation to predict the expected carbon dioxide emissions for the following gross domestic products. So in this case, we're told that we have $1.2 trillion, and we want to know what we can expect our carbon dioxide emissions to be with that $1.2 trillion. To do this, we're going to use the equation, and we're going to substitute that 1.2 into our x variable, and then we're going to solve for y. So we're going to evaluate, and we're going to find that it's going to be approximately 337.67. And what that means is when the gross domestic product is 1.2 trillion, the CO2 emissions are going to be about 337.67 million metric tons. So we're going to be finding this equation of best line fit using our calculators. So we have this example here. We want to find the equation of the line that best fits the data to estimate the number of calories in a fast food that has 14 grams of fat. So first we want to show a scatter plot for the given data. So now we're going to put in the data into the calculator, and we're going to get the scatter plot. So to do that, you're going to go to the stat number 1, and you're going to enter in the data just like the other examples. So your list 1 will be your fat grams, which is the x variable. Your list 2 will be the calories, which would be your y values. Once you enter in the list, then you want to go to your stat calculate the number 4. So we're going to go into the stat calculate. Now in here, I want to show you that there's one extra step you will need to take in order to get the scatter plot to have the linear line in it. So to do that, you want to store that y equation into the store regression equation option. So in the newer calculators, you'll have that store REGEQ, and you want to put that y1 in there. So where you find y1 is in your VARs menu. So you're going to go to VARs, and this is the menu you're going to see, and you want to arrow over to the y VARs. Once you arrow over to the y VARs, you'll see these options, and you want to choose the option 1, which is function. Once you choose option 1, you're going to see the y1, y2, and so on. We want the y1 in there, so you're going to hit enter, and it will pull in y1 into that stored option. Now if you have the older calculators, you're going to have to type in the L1, comma L2, comma, and the y1. And you're going to have to go through the same process to get that y1. The L1 and L2, you do the second key and number 1, second key number 2. But for the y1, you're going to have to go through this process. Now once you have that entered in, you're going to hit enter, and then you're going to find your linear regression equation. So here is your A value, which will be your slope. So you would substitute it into the A into the equation. And then the B value will be your y-intercept. And then you see your correlation coefficient. And remember, the correlation coefficient gives us the strength of this linear regression. So here is the equation that is the best fit for this data. So we end up with our y equals 13.607x plus 150.87. And our correlation coefficient is 0.972. So now we have the equation. And the equation of the line that best fits and the correlation coefficient, and we're going to estimate the calories. But first, we want to see what the scatter plot will look like. So once you have the data in, you want to go to graph the linear regression. To do that, you're going to use the zoom button, and you're going to zoom to number 9, the one that says zoom stat. Once you hit enter, you're going to see your scatter plot with the regression line in the picture now. So you can see how closely the data is to that linear equation. Once you have that, you can do any prediction for the values you're asked to evaluate. So in this case, we're asked to estimate 14 grams. Well, to estimate using the calculator, you're going to go into that Y1 option into the calculator. So you go to your vars, arrow over to Y vars, choose the function, and choose the Y1 function. Once you have the Y1 in your screen, you're going to need to use parentheses, type in the data, in this case 14 that we want to predict, close the parentheses, and then hit enter. Once you hit enter, it's going to give you that value for that equation. So in this case, we would expect that we would have 341 calories when we have 14 grams of fat. So that's how you would do a predictive value using the calculator. Pause and try. So here is what you should have gotten. Our linear regression line is y equals the 32.333x minus, don't do two signs, it's either plus or minus, and in this case we ended up with the negative b value, so it's going to be minus 64,105. Our correlation coefficient is positive 0.996, which is a strong correlation, and then what we could expect for 2010 will be 885 billion. So now we're going to do some hypothesis testing for the population correlation coefficient rho. So we want to test to see if the sample correlation coefficient is adequate for the population. So the hypothesis test is used to determine whether the sample correlation R provides enough evidence to conclude that the population correlation coefficient rho is significant at a specific level of significance or alpha. So when we're stating the hypotheses, it's always based on the alternative. So when you have rho is less than 0, well, that is significant negative correlation. When you have rho is greater than 0, it's a significant positive. And when you have rho is not equal to 0, significant correlation. So we can state that there's a significant correlation if when we do our testing, our null hypothesis is rejected. Now with this particular textbook, we are only going to have the two tail tests, and our claim will always be on the alternative. So we're always testing to see if there's significant correlation. So the test statistic, or the t-test, and p-value is found by using this formula, and this formula can be calculated directly from the calculator. So if you have a newer calculator, under your stat option, you arrow over to test, you'll find it under the menu option F, which is Lin Regression t-test. If you have an older calculator, it's going to be under E, your Lin Regression t-test. Now you're going to have to arrow down to find it. So when you do that, arrow until you get to it. Using the p-value from technology to interpret the sample correlation coefficient. So to use the p-value and the level significant alpha, you're going to do the following. If we have a p-value that's less than or equal to your alpha, you're going to reject the null hypotheses. And if you reject the null hypotheses, that means that you can support the claim of a linear correlation. But if the p-value is not less than or equal to alpha, or it is a false statement, then you fail to reject the null hypotheses. So if you get a false statement where your p-value is not less than or equal to alpha, then you're going to fail to reject the null hypotheses. Well, if you fail to reject the null hypotheses, what that means is that that does not support the claim of linear correlation. So you're looking to see, do we have linear correlation? The claim, again, will always be on your alternative statement. Here's the process for using the t-test for rho. You want to first state the null and the alternative statement. And again, the claim will be on the alternative. Identify alpha. And then once you have alpha, you want to find your p-value because you're going to compare it to alpha. Find the p-value by going to that stat option and arrowing over to test. Choose the linear regression t-test. Enter in the data, and then you're going to test your p-value. If your p-value is less than or equal to alpha, then you're going to reject the null. Otherwise, it fails to reject. So if you reject the null, then it supports the claim. If you don't reject the null, it does not support the claim of linear correlation. So here's an example. We had sample of 10 families revealed the following figures for family size and the amount spent on food per week. So we have size and dollar. Can we conclude that there is a positive association between the amount spent on food and the family size? It wants us to use a level significance of 0.05. So what we're going to do is we're going to state the null and the alternative. And again, it's going to be a two-tail where we have rho is equal to 0 as our null, and the alternative is rho is not equal to 0. Then we're going to identify alpha, and that is the 0.05. Now we got to find our p-value and our test statistic. To do that, we're going to have to first enter the list into our calculator. So we're going into that stat button, choose edit, and then type in the list. In list 1, you'll put the size. In list 2, you'll put the dollars. Once you have the list entered in, then you can go to stat, test, and find that linear regression t-test. Once you have that, then you're going to hit enter, and it's going to give you this menu option. Make sure that your X list has your L1 in it, your Y list has your L2 in it, and that you have highlighted the two-tail row test. Hit calculate, and then you'll come up with this answer. So we have our test statistic, that t-value, and you have your p-value. So in this case, we have test statistic would be that 2.062, and our p-value is 0.073. So you see here our p-value when we test it to see if 0.073 is less than or equal to 0.05, it's a false statement. And because it's a false statement, we fail to reject the null. And if we fail to reject the null, there is not significant evidence to support the claim that there is a linear correlation. Pause and try. So we state our null and our alternative, a two-tailed test. Your p-value here was 0.0099. The test statistic is a negative 5.858. And then we have our correlation coefficient as a negative 0.959. Our p-value is less than or equal to 0.05. So we have a true statement, which means we reject the null. Because we're rejecting the null, there is significant evidence to support the claim that there is a linear correlation.